Well, hello everybody. Welcome to another day of Math 300. I'm glad you're here. Alright, so today what we're going to be doing is some more proof stuff. We're going to talk about a new proof technique. In particular, we're going to be talking about proof by induction. So, what is proof by induction? Well, the idea is that what we're going to have is we're going to have a base case or a basis. We're going to say, okay, if this theorem true for one case? So instead of trying to prove some theorem for all cases, we'll try to prove it's true for one case. And then what we'll do is we'll assume it's true for the nth case and prove it's true for the n plus 1 case. If we can do this, what ends up happening is that, well, we know it's true for the first case. Because the nth case implies the n plus 1 case, the first case implies the second case. The second place implies the third case. The third place implies the fourth case. And so what you get is that the theorem will then be true for all n and n. And so every case implies each other. It's a lot like dominoes set up where you knock the first one down and it knocks the next one down. And so by showing one case, then showing that one implies the next, you get that everything's included. So to start with, we're going to look at an example here. We're going to say if n is an n, then the sum from 1 to n of 2i minus 1 is going to be n squared. Alright, so let's look at that. The base case here is because we're starting at n equals 1, or if we're trying to sum from 1 to n, we're going to use n equals 1, so we're going to get our base case is n equals 1, and so what we want to show is that the sum from n equals 1 to I equals 1 to 1 of 2i minus 1 is equal to, and then eventually we want to get that this is equal to n squared, and so that's going to be 1 squared. So the point here is, okay, I'm picking the first case out. I let n equal 1. So I'm finding the sum from 1 to 1 of 2i minus 1. And I want to show that that's equal to 1 squared. Notice I'm not assuming these are equal. I'm going to write out some type of list here so that I make sure they're the same. But if I plug 1 into this, what I get is 2 times 1 minus 1 is going to be 2 minus 1 is 1. But then 1 squared is 1. So what we've shown is that at least for n equals 1, the theorem is true, that the sum from 1 to n of 2i minus 1 is indeed equal to n squared. Now that we have that for n equals 1, what we're going to do is move on to the induction hypothesis. So what that means is we can assume that we'll say the sum from I equals 1 to k of 2i minus 1 is equal to k squared. And what we have to do is we have to show that the sum from I equals 1 to k plus 1 of 2i minus 1 is equal to k plus 1 squared. So again, the idea is that we assume the theorem for the kth term, and we show that that implies the theorem for the k plus 1 term. So that means that since we have it's true for 1, it'll be true for 2, 3, 4, and so on. So we have to say, okay, well, how am I going to do this? So I get to assume this, I have to show this. So now as I start off, I'm going to end up needing some more room here. So I'm going to start back up here, and I'm going to say the sum of I equals 1 to k plus 1 of 2i minus 1 is equal to, and eventually we want to get out our k plus 1 squared. So the idea is to take this, and I'm going to write a bunch of things so that eventually I'll get this out. So now I have where I'm starting, I have my goal, and so I want to be able to get from here to here. Alright, so now how do I do that? Well, the first thing I'm going to realize is that I have to be able to use what I had before, is that the sum from 1 to k of 2i minus 1 was k squared. And so with sums, an induction proof actually lends itself very well, because the sum works out to be, well, this is just the sum from I equals 1 to k of 2i minus 1 plus, and then I can plug in the k plus 1 term, so I get 2 times k plus 1 minus 1. So if we're doing an induction proof with sums, the nice thing is, okay, well, if I'm going to add from 1 to k plus 1, I can instead add from 1 to k, and then I just add in the k plus 1 term. So what I end up with is a nice step where I get to use my induction hypothesis, because that says that this is just equal to k squared. So if I write that out as k squared, I get k squared plus, and I'm going to simplify this, I get 2k plus 2 minus 1 is going to be k squared plus 2k plus 1. And so I've just taken this and I've simplified it algebraically, and I get k squared plus 2k plus 1. Now notice that, well, I can just factor here. So if I factor k squared plus 2k plus 1, that is just k plus 1 squared. So what we get is, okay, if this is true for the sum from 1 to k, then it has to be true for the sum from 1 to k plus 1. Hence, it has to be true for all natural numbers. So the sum from 1 to n of 2i minus 1 must be n squared, as our theorem stated. And so we've used an induction proof to show our theorem. Do you guys have any questions there? I see Dylan, I missed your text. Yes, so we want to split the sum. That's exactly what we did. Good job on that one. All right. So another type of proof here, instead of sums, we can also work with division, or showing things divide other things. And so what I want to show here is that if n is a non-negative integer, then 5 divides n to the 5th minus n. All right. So if I want a non-negative integer, that means that my base case should actually be the smallest non-negative integer. So the base case here is actually going to be n equals 0. So what we'll do for the base case is we'll let n equal 0. Then what we have to do is we have to show the theorem for that, and that is I have to show 5 divides 0 squared minus 0. So instead of n squared minus n, I'm just substituting in n is currently 0. So I have to show 5 divides 0 squared minus 0. Now, what I want to point out here is just, well, if I want to show this, what I have to show is that 0 squared minus 0 is equal to 5 times some integer. But notice that 0 squared minus 0 is just equal to 0. So that is 5 times 0. So indeed, we do have that 0 squared minus 0 is 0, which is 5 times 0. So therefore, 0 squared minus 0 is 5 times an integer. So 5 divides 0 squared minus 0. Here again, our base case is actually pretty simple. We just have, oh, well, if I plug in n equals 0, I'm trying to show 5 divides 0. Well, 5 divides 0 because 5 times 0 is 0. And so we have, okay, this theorem is true for the 0th case. Now what we're going to do is assume that this is true for the kth case and show it has to be true for the k plus 1 case. So what we get is we get to assume 5 divides k to the 5th minus k, and I have to show that 5 divides k plus 1 to the 5th minus k. Is that all making sense so far? Any questions at all? Alright, so what does it mean for 5 to divide k to the 5th minus k? Well, that means that k to the 5th minus k is equal to 5 times some integer. I'll go ahead and say k1 here. So I do want to point out that I'm using k's, but k1 is different than k. So 5 times k1 is indeed equal to k to the 5th minus k. And what I want to show is that k plus 1 to the 5th minus k plus 1. Sorry, this should be a k plus 1 because I want to substitute in k plus 1 where there was an n. We want to show that that is equal to 5 times k2 for some integer k2. So now notice what I'm doing is setting this up just like I have any other proof. I get to assume this, I have to show this. The assumption is equivalent to this, the then or the showing is equivalent to this, and then I have to somehow make up the middle terms here. So I have to find how to connect from here to here. Well, notice that we're trying to show that this is equal to this. So what we'll do is we'll start on the left-hand side, we'll do some arithmetic and hopefully simplify it so that we get the right-hand side out. Alright, because I'm going to need more room, hopefully we can remember this. So I'm going to go back and say, well, what is k plus 1 to the 5th minus k plus 1? Well, now if I need to find k plus 1 to the 5th, what is that going to be? Well, if I want to find this directly, that actually takes a little bit of work, but it isn't too bad because we can do what is we can actually use Pascal's triangle that we learned about earlier, right? And so if I write out the rows here, I get 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So what we get is that k plus 1 to the 5th is 1 times k to the 5th. Plus 5 times k to the 4th, plus 10 times k to the 3rd, plus 10 times k squared, plus 5k, plus 1, and then we're going to subtract k plus 1. All right. So there's a lot going on there, so I'm going to need even more room. But the point is that even though it's to the 5th, we can't actually just write out k plus 1 to the 5th is k to the 5th, 5k to the 4th, 10k cubed, 10k squared plus 5k plus 1. And we could do that using our binomial theorem or using Pascal's triangle to find those coefficients quickly. Now what we want to do here is we want to simplify this. So the first thing I'm going to notice is that I have a plus 1 here, and I have a minus 1 here. So those are going to cancel. And what I'm left with is, well, I can take 5k and I can subtract k to combine these. But remember that I knew something about k to the 5th minus k. So I'm actually going to notice that I have a k to the 5th minus k. So I'm going to write k to the 5th minus k. And then I'm going to write the remainder is 5k to the 4th plus 10k cubed plus 10k squared plus 5k. Now, remember that the reason why I wanted to do that is because I already know that that is equal to 5 times k1 for some integer k1 by my induction hypothesis. So that's what we get to assume is that this is a multiple of 5. But now, what happens is, if I actually look at the rest of these terms, notice that I can indeed factor out a 5 because each of these terms is divisible by 5. So what I get is 5 times k1 plus k to the 4th plus 2k cubed plus 2k squared plus k. So I indeed can factor 5 out of all these terms, and so what I would say here is that this is 5 times, and this big term here, I'll just call k2. So what I found is that k plus 1 to the fifth minus k plus 1 is indeed divisible by 5 because it's equal to 5 times some integer. So remember, that's what we were trying to prove, was that we got to assume that k to the fifth minus k was divisible by 5. We were able to prove that k plus 1 to the fifth minus k plus 1 was divisible by 5. So what we get is that our theorem is now true. We've shown it's true for 0. We know that if it's true for k, it's true for k plus 1. So 0 implies 1, implies 2, implies 3, implies 4, implies 5. And therefore we get this is true for all natural numbers. So k to the fifth minus k is indeed always divisible by 5. And so I just want to point out that if you look at the homework from the book, a lot of the ones they focus on are either sum ones like this, so sums, or division ones like this. And so you'll have practice working with both of those. And both of those follow similar processes. So that is, with the sum one, we break it up into 2 terms. So we add up the first k terms, and we break off the next term. And then for the division one, we recall that the division works in the kth place, and we take the k plus 1 case, and we do some algebraic manipulations to simplify, and we're able to show that it works for the k plus 1 case. You guys are really quiet today. Are you guys actually there? Maybe I should make you type something. All right. Thank you, Dylan. I appreciate you talking to me. I think you're the only one, though. I see that there are 9 people on right now. Oh, Hannah and Malik and Harrison. Thank you, guys. I appreciate it. Oh, all right, good. So you are there. I guess you're just getting everything, so you don't have any questions. What I wanted to point out next is we're actually going to look at another example here. And the reason why I want to do these examples is because actually these ones come up in Calculus 1. And I don't spend a lot of time trying to prove them because I kind of say, hey, if you want to know these, you can either come by during office hours or see them in a future class. So this is the future class where I get to prove all the stuff that I didn't do in calculus. I think I actually did do this proof for my calculus class, but the next one I haven't. So what I have here is I want to show that the sum from 1 to n of I is equal to n times n plus 1 over 2. And so if you're trying to remember where did this stuff come into play, it's when we were talking about Riemann sums. We had to find sums and then simplify them. And so this one came up. So let's go ahead and look at that. And we'll use an induction proof to show that the sum from 1 to n of I is n times n plus 1 over 2. All right, so the first thing we want to do is just show the base case. So we're going to let n equal 1. So we want to show the sum from I equals 1 to 1 of I is equal to, and I want to get out. This should be 1 times 1 plus 1 divided by 2. So my formula is n times n plus 1 over 2. I'm just substituting in 1 for n in each case. I want to make sure that I get the same thing. So if I sum from 1 to 1 of I would plug in 1, I get 1. But 1 times 1 plus 1 is 2 over 2 is just 1. So it does work out that 1 is 2 over 2 is equal to this. So we have that the base case is true. So our sum works out for n equals 1. All right, with that, we're now going to go through and say, well, let's suppose that the sum from I equals 1 to k of I is equal to k times k plus 1 over 2. And we want to show that the sum from I equals 1 to k plus 1 of I is k plus 1 times k plus 1 plus 1 over 2. So that's our goal, is we get to assume the induction hypothesis, that is, this is true, and I have to show that this is true. So I want to show that I get out the formula works for the k plus 1 term if it works for the k term. So what we have is a sum. So if I'm going to do a sum proof by induction, as I said before, I'm going to start off with the sum from 1 to k plus 1, and I'm going to just break this up into two terms. So I'm going to add from 1 to k of I, and I'm going to add the k plus 1 term. So if I plug k plus 1 in for I just get k plus 1. So I get the sum from 1 to k of I plus k plus 1. Now, using the induction hypothesis, what I get is, well, this is just k times k plus 1 divided by 2 plus k plus 1. Now, I'll leave this up here to know that's kind of where I'm headed. And so somehow I have to try to take this and manipulate it so that it instead looks like this. So the first thing I would see is that, notice here I have two fractions, but here I have one. So I wanted to make these into one fraction. So the way I would do that is find a common denominator. So I'll multiply this by 2 over 2. And then I can combine those into one fraction. So I get k times k plus 1 plus 2 times k plus 1, all divided by 2. Now, notice what I want is this. So what I can do here is, if I look at the top, each of these terms has a k plus 1 on it. So I can factor out the k plus 1. And what I'll get is k plus 1 times k plus 2. But instead of writing that down, notice that this is just k plus 2. So I get k times k plus 2 divided by 2, which is exactly what I wanted. So now I know that, yes, indeed, the sum from 1 to n of I is equal to n times n plus 1 divided by 2, and that will be true for all natural numbers n. All right. Now, here's one thing I want to point out about the induction proof is that we have now proven that that is true, but we really didn't see where that came from. Where does the formula come from? How did we find it? Well, for induction, you really just need to guess what it is, and then you can use a proof to show that it has to be true, but it doesn't really give you any insight into why it's true. And so a lot of times using induction is saved for things that are just more difficult proofs. If we can, we'd like to do some type of constructive proof to show that, say, the sum from 1 to n of I is equal to n times n plus 1. So one way we could do that, just to give you another example here, is, well, what we can do is we could take 1 plus 2 plus 3 plus 4 up to n. So the idea is that the sum from 1 to n of I is equal to this. And so we can stare at that a while, and we can try to determine what is that going to be, or how can I prove that that is what I claim it is. All right, I'll let you guys stare at it. Do you guys see how to prove this? Well, just as a note, some historical facts here. When Carl Gauss was in middle school, basically, or elementary school, or that area, his teacher was lecturing, and he was being annoying, as I'm sure Gauss was sure to do. And so the teacher wanted to give him some busy work just to keep him from annoying the class. And so she told him to go up and sum up from 1 to 100 of I. So add up the first 100 terms. And so it took him all of about 30 seconds to look at it and come back with the correct answer of 5,050, which just upset the teacher even more. But that just shows it was just the idea that, well, instead of actually adding all of those things up, he just came up with an ingenious way to realize what that's going to be, so he didn't actually have to go through all of the hard work. That, and if an 8th grader can do this,
It just makes me feel a little less intelligent when I look at this. All right. Anyway, the idea and what he did and how he found this was that he just said this is also the sum from 1 to n of I is also equal to n plus n minus 1 plus n minus 2 plus 1. So what he realized is that if I write this sum and I reverse the order, it's going to be the same thing. But now if I add these, what I end up with is 2 of these sums are equal to, well, in this case, I get 1 plus n is n plus 1. 2 plus n minus 1 is just n plus 1. And then I get plus n plus 1. And for each of these terms, I'm just going to get n plus 1. And so what you'll see is that 2 of the sums are just n plus 1, n plus 1, n plus 1. And so if we want to count these up, notice that there are, well, we've counted those. There are exactly n of those. So 2 sums are equal to n times n plus 1, which is actually really cool, and it actually feels a lot more constructive and really shows why this is happening. Is, oh, okay, if I rearrange these, I can add them together. I keep getting n plus 1s. So if I want 1 sum instead of 2, I divide by 2, and so I get out exactly my answer. So there you go. The point here is that a lot of times if we can come up with constructive proofs, they kind of feel nicer. They give you more insight into why things are true than an inductive proof would, but an inductive proof shows that it actually is true. So if we come into a place where it's difficult to show that this is always true, if we can end up using induction, it's a nice way to get that, okay, well, at least we know that this has to be true. All right. The next proof I want to do is another one that I talked about in calculus, but while I gave the proof for the first one in calculus, I actually didn't give the proof for this one in calculus, and that is the sum from 1 to n of I squared is indeed equal to, I'm trying to read it so that I don't write it down incorrectly, n times n plus 1 times 2n plus 1 divided by 6. Now, yes, you can constructively prove this one as well, but it becomes much more difficult. So instead what we're going to do is actually just use an induction proof. So that's the reason why I didn't do this proof in calculus, is that it requires a proof by induction. And in calculus, you don't know proof by induction. So now that we do, we will actually prove this. The first thing we need to do is if we let n equal 1, that's our base case, well, we're going to get the sum from 1 to 1 of 1 squared is 1. So that's 1 squared is 1. On the other hand, we're going to get 1 times 1 plus 1 times 2 times 1 plus 1 divided by 6. And so if we calculate this, we get 1 times 2 times 3. 2 times 3 is 6, divided by 6 is indeed 1. So this does work out for the base case when n equals 1. So now what we need to do is we'll assume that this is true for the kth term, and we have to show it's true for the k plus 1 term. So I'm going to start off with, let's say the sum from 1 to k plus 1 of I squared is equal to, well, if we're going to assume that it's true for 1 to k, we'll get our formula out. What we're going to have to do is break this up into 2 sums. So this is the sum from 1 to k of I squared plus, and then I can plug in k plus 1 for I, and I get k plus 1 squared. So what do I get now? Well, remember this, we're assuming by the induction hypothesis that this is indeed equal to k times k plus 1 times 2k plus 1 all over 6. So plus k plus 1 squared. Now, eventually, I'll write down our goal here is to get something that looks like k plus 1. So plug in k plus 1. And then k plus 1 should be k plus 2. And 2 times k plus 1 should be 2k plus 2 plus 1 is 2k plus 3 divided by 6. So to know where we're going, that's what we want. So I want to rewrite this so that it ends up looking like this. And again, the first thing I notice is that I have one fraction here, whereas I have two up here. So I'm going to combine these. So I'm going to find a common denominator. And what I would get is k times k plus 1 times 2k plus 1 plus 6 times k plus 1 squared, all divided by 6. All right, so now I still have work to do in here. I wish my chalkboard was bigger, but it's not. So I'm going to have to create some room. And somehow I have to get from here to here. Well, notice that I want a k plus 1, I want a k plus 2. So what I'm going to notice here is that both of these terms have a k plus 1 in. So I'm going to factor that out, and I get k plus 1 times, and then here I'm going to get k times 2k plus 1 plus 6 times k plus 1. So I factored out the k plus 1. The remainder was k times 2k plus 1 and 6 times k plus 1. And then this is, again, all divided by 6. All right, if I do a little bit more simplification, I get, well, I can distribute this out. I get 2k squared plus k plus 6k plus 6 divided by 6. If I combine like terms here, I get 2k squared plus 7k plus 6. Now, again, remember, this is our goal. So it looks like all I have to do is factor this. So if I factor that, notice that I'm going to get one term that looks like 2k plus something, and another term that looks like k plus something, because these two have to multiply by 2. These two have to multiply by to get out 6. And then when I cross multiply, I have to get out 7. So if I go plus 3 and plus 2, I get 2 times 1 is 2, 3 times 2 is 6, 2 times 2 is 4, plus 3 is 7. So that is the correct factorization. But notice all I've done is rewritten this in a different order. So we have indeed gotten that our sum will work out for the k plus 1 case if it works for the k case. Therefore, since we've proven it's true for the first case, it'll be true for all n. So therefore, we do get that our formula is true for all n. Now again, why is that true? Well, it's true because of the induction proof, but where does that come from, or how did we find that formula? Well, the formula was a lot of guess and check and try to figure it out, and somehow we came up with the correct answer, and then we just proved it was true. So there wasn't a nice outlining of, well, let's follow the ideas and come up with a constructive proof. It was, okay, I think it looks like this. Therefore, I'm going to check that pattern, and I'm going to check that pattern using an induction proof. So now that I've done the induction proof, I know that that pattern has to be true. Does that make sense to everybody? Any questions in there? All right. Here's one more theorem that I want to look at because it is really interesting. And let's suppose that I have a1 through an are integers. And I'm going to say n is greater than or equal to 2. Well, if p is prime and p divides the product of those integers, what I want to say is that p will divide one of the terms. So now what I'm doing here is actually showing that, well, if I have, and now here what I really mean is if I have an irreducible number, meaning that I can, if it's written as the product of two numbers, it's only one in itself. And so I want to show then that if it divides a product of terms, it has to divide one of the terms. And so what I get here is that really, using the terminology I used in classes, I'm trying to show that every irreducible is indeed prime. So how are we going to do this is, well, we're going to have to work through an induction proof. So we're going to say our base case is going to be 2, and then we're going to have to show this for the nth case. All right. So I need some more chalk. Let's suppose that P is prime and it divides A1 times A2. So we're going to let n equal 2. So if P divides A1 times A2, what I want to show is that P either divides A1 or P divides A2. So if P divides A1, I'm done, right? So if P divides A1, I get that P divides A1 or A2. So I'm just going to say then done. So if we want to prove this, we can assume that P does not divide A1. Because if it did, we'd be done. We don't have to do a proof. But the interesting proof is if P does not divide A1, well then we have to show that P divides A2. All right, now if P does not divide A1, notice that then, what is the greatest common divisor of P and A1? You guys help me out here. Maybe you can give me the answer. P does not divide A1. So what is the greatest common divisor of P and A1? Well, the only divisor of P is 1 or P, right? Now, I have no idea what divides A1, but a bunch of stuff can, or nothing can, or whatever. But, thank you, Hannah. So the greatest common divisor can't be P because P doesn't divide this, so it has to be 1, which is exactly what you said. Very good. So the idea is that the greatest common divisor of these two must be 1. Now, before break, I know this was a long time ago, we went through this actually really long, complicated proof to show something that probably didn't seem all that significant. But if you notice that, what we said was that if the greatest common divisor is equal to something, then I can find, let's say, a k and an integer k, where k times p and an integer l, a times l is equal to 1. So that is, since the greatest common divisor of p and a1 is 1, there has to exist integers k and l such that kp plus la1 is indeed equal to 1. Now, if you don't quite remember that, I don't blame you. It's been a long time. But instead of going through that entire proof again, I'll just refer you back to that section when we're talking about this. And we know that this has to be true. All right. Now, why is this helpful is, well, notice what I can do is I can multiply both sides here by A2. And if I multiply both sides by A2, what I get is KPA2 plus LA1A2 is equal to A2. Now, if I'm looking at that, what I notice is that there's a P here, so I can factor that out. So, also though, what do I know about A1 times A2 is P divides A1 times A2. So A1 times A2 is really just P times some integer, we'll say M. So this is instead of A1 times A2, this is really just P times M. I'm just making M up, but the point is I know it divides this, so P times M has to be equal to A1 times A2 for some M. So what I get is that A2 is now equal to KPA2 plus LPM, but notice that both of those terms have P in it, so I can factor them out. So what's left? Well, Ka2 plus Lm is just an integer, so what we've just shown is that P times an integer is equal to A2, therefore P divides A2. Hence, if P divides A1, then we're good. If it doesn't, then the greatest common divisor is 1. Therefore, it will have to divide A2. Therefore, P either divides A1 or A2. It could technically divide both. There's nothing wrong with that, but it has to divide at least one of them. Now, I just want to point out that was the base case. That was actually rather complicated. So that's kind of scary for the general case. Well, let's see what that looks like. What we get for the induction hypothesis is that we get to assume that if this divides A sub k, then P divides A sub I for some I in here. And what we have to show is, let's assume that P divides A sub 1, A sub 2, A sub k plus 1. So that is, instead of having k terms, I'm going to have k plus 1 terms. I want to show that P divides one of the A sub i's. All right, so how do we do this? Well, actually, this is a really cool proof because the base case is actually more complicated than the general case, because what we notice here is that, well, if we just break this up into terms, we have two terms here, and P divides this, or P divides this, because the product of these terms is just an integer. So therefore, by the base case, since it divides the product of two terms, it has to divide either this or this. If P divides this, then we've shown our theorem and we're done. Otherwise, P divides this. But if P divides this, then by our induction hypothesis, it has to divide one of the terms. Therefore, we're done. So, P either divides this or this. If it's this, then we're good. If it's this, then we're good by the induction hypothesis. And so I really like this proof because it shows that the base case can actually be much more complicated than the general case. And so once we have the base case, this one falls out pretty quickly. All right. Exactly, Dylan. The k plus 1 here didn't make that much of a difference because we could break it down into two spots, and we really just had the base case again. But we still do have to check it. So the idea is that if I have a prime dividing any number of terms, it has to divide one of those individual terms, or the product of any terms. It has to divide one of the terms. All right, let's see. I think I'm going to leave it there. We still have 8 minutes left, but we're going to start strong induction next time. So I'll just pick up with strong induction on Friday, so that, because I don't think we'll be able to finish this next proof in the next 8 minutes. So what we learned today was we went through and we saw that. What we saw today was that we could go through, or we could use an induction proof where we prove the base case, and we have to prove then we get to assume the kth case, we have to show the k plus 1 case. Next time we'll continue with this. We're just going to work in a little bit more general terms. And so I'll leave you guys there, and thank you for watching and actually making it to class. I'll see you guys on Friday.